Dear students, welcome back to my YouTube channel Rahman Chemistry Coaching Academy. In continuation of our lecture number 13 on base 10 theory, today we will discuss and explain the remaining part of the base 10 theory in our this lecture number 14. Look at to the structure of cyclopropane, which acts as an equilateral triangle with bond angle of 60 degree. This means that the cyclopropane ring has been compressed from the normal tetrahedral bond angle of 109 degree 28 minutes by an extent of 24 degree 44 minutes on each side. Due to this compression of the bond angle from the normal tetrahedral bond angle, the cyclopropane is highly unstable ring with more angle strain. In addition to it, all the six hydrogen atoms and three carbons of cyclopropane are eclipsed due to the planar nature of cyclopropane, and hence this eclipsing nature of these six hydrogen atoms and these carbon also contribute much to the instability of cyclopropane. Now look at to the structure of cyclobutane, which acts as a square with bond angle of 90 degree. This means that in cyclobutane, the bond angle has been reduced or compressed to 90 degree from the normal tetrahedral bond angle of 109 degree 28 minutes by an extent of 9 degree 44 minutes on each side. This caused the cyclobutane to be a stable ring with less angle strain. Additionally, the stability of the cyclobutane ring is due to its pocket nature ring conformation, in which one carbon out of the four carbon atoms of cyclobutane move out of the plane of the four carbon atoms, while the remaining three carbon atoms remain in the plane to relieve torsional strain caused by eclipsing hydrogen atoms and carbon atoms in planar cyclobutane. This caused the cyclobutane to be more stable than cyclopropane. In case of cyclopropane, which acts as a pentagon in which the bond angle has been compressed or reduced from the normal tetrahedral bond angle of 109 degree 28 minutes to 108 degree with an extent of 0.44 minutes on each side. This caused the cyclopentane to be a highly stable ring with less angle strain. Additionally, the stability of cyclopentane is also due to its open envelope conformation, in which one carbon moves out below the plane of the pentagon, relieving torsional strain due to the eclipsing hydrogen atoms present on all five carbon atoms of cyclopentane. The torsional strain still exists due to interactions of the eclipsing hydrogen atoms present on the remaining four carbon atoms in the open envelope conformation of cyclopentane, causing cyclopentane to be less stable than cyclohexane. In case of cyclohexane, which acts as a hexagon with bond angle of 120 degree and which has been widened or extended by minus 5 degree 16 minutes on each side from the normal tetrahedral bond angle of 109 degree 28 minutes. This caused the cyclohexane to be a less stable ring with high angle strain, but practically cyclohexane can adopt pocket chair conformation and thus relieve much of its torsional strain and angle strain, and thus is more stable than cyclopentane. This table shows the cycloalkanes, their ring sizes, the desired angle, the actual angle alpha, the deviation from the normal tetrahedral bond angle 109 degree 28 minutes, and the structure of cycloalkanes. Now look at to these cycloalkanes. and their stability order. According to Baeyer's strain theory, cyclopentane, due to less angle strain, is more stable cycloalkane as compared to cyclopropane, cyclobutane, and cyclohexane. The ring systems, smaller or larger than cyclopropane, are unstable due to higher strain, but in reality, cyclohexane is more stable than cyclopentane. Thus, the order of the stability of cycloalkane is that applications of Bayes strain theory. Bayes strain theory has some applications. These are: number one, Bayes strain theory will explain the instability and ring opening reactions of cyclopropane. Number two, this theory also explains how cyclobutane undergo ring opening reaction under some rigid conditions and how it is more stable than cyclopropane. Number third, it also explains why cyclohexane and higher cycloalkanes do not undergo ring opening reactions even though they are more stable and resembles to open chain alkanes in their reactions by substitutions. Number four, based in theory satisfactorily interpret the exceptional reactivity of cyclopropane, cyclobutane, and cyclopentane, but it is not valid for cyclohexane and higher cycloalkanes. Number five, Bayer proposed that rings smaller or larger than cyclopropane were unstable, and due to this instability, the 3 and 4 member cycloalkanes ring undergo ring opening reaction. This instability creates great difficulty in the synthesis of higher cycloalkanes. Limitations of Bayer strain theory. Bayer strain theory has some limitations. These are: number one, Bayer strain theory is capable only to explain the effect of angle strain in smaller ring cycloalkanes but fail to explain in larger ring cycloalkanes. Number two, according to Bayer strain theory, cyclopentane is much stable than cyclohexane, but practically it was reversed, that cyclohexane is more stable than cyclopentane. Number third, Bayer strain theory is not applicable on higher cycloalkanes, that cyclopentane, cyclohexane, and cycloheptane, etc. It is because these cycloalkanes possess negative strains and are much more stable. Number four, higher cycloalkanes are usually not planar but rather puckered in nature and thus eliminate angle strain. Number five, like cyclopropane, which gives ring opening reactions very easily due to its instability, the higher cycloalkanes do not undergo ring opening reactions due to their stable nature. Number six, Bayesian theory is partially correct. This theory is wrong for the reason that it take into consideration that all the cycloalkanes are planar in nature. It doesn't take into account torsional strain, the strain due to eclipsing of bonds on neighboring atoms. Bayesian theory doesn't take into account the steric strain, the strain due to repulsive interaction when atoms approach each other too closely. Number 8, in cyclopropane, cyclobutane, and cyclopentane, angle strain occur due to which cyclopropane and cyclobutane are strained. Cyclopentane is more strained while cyclohexane and higher cycloalkane are strain free. Look at to this graph. This graph shows the relationship for the energy release per CH2 group in strained ring and strain free CH2 on combustion. From the look of this graph, it is clear that the energy released on combustion by CH2 in strained ring is higher than that of strength-free CH2 group. Again, look at to this table. This table shows heat of combustion of straight chain alkanes. From this table, it is clear that the difference in heat of combustion between any two members of the series are very nearly constant at around minus 660 kilojoule per mole. Let's we assume as is reasonable that there is no strain in straight chain alkanes, then each extra methylene group C2 group contribute an average of 658 kilojoule per mole to the heat of combustion per alkane. A cycloalkane C2 whole N is simply a number of methylene groups joined together. If the cycloalkane is strain-free, then its heat of combustion should be N multiplied by 658 kilojoule per mole. However, if there is some strain in the ring which make the rings less stable that raises the energy of the ring, then more energy will be given out on combustion. Now let's put all these together in this graph showing per each ring size. Number 1 the angle strain per CH2 group, and number 2 the heat of combustion per CH2 group. Points to be noted in the green colored graph: the greatest strain is observed in 3-member cyclopropane, which decrease rapidly with increase in ring size and reaches a minimum per cyclohexane and not per cyclopentane. As was predicted, the strength then increases and reaches a maximum at nonane and then decrease once more. The strength doesn't go on increasing as the ring size increases, but instead remain roughly constant after ring with number of carbons up to 14. Cyclohexane with 6 carbon atoms and larger cycloalkanes with number of carbon atoms in the ring greater than 14 all have heat of combustion per C2 group of around 658 kilojoule per mole, the same value as that of C2 group in a straight chain alkane. That's why they are essentially strain free. So thank you for watching my this video lecture. If you find this video interesting and informative, then please like, share, comment and subscribe my channel for more videos.